The universe is alive. It's a place of constant motion and change, where stars are born, galaxies collide, and black holes devour matter with insatiable hunger. What if this cosmic dance eventually winds down? What if the universe's ultimate fate is not a fiery explosion or a grand collapse, but a slow and chilling fade into darkness? This is the prospect of the Big Freeze. A cosmological scenario where the universe continues to expand forever, growing colder, darker, and emptier with each passing eon. Imagine a universe where stars eventually burn out, galaxies drift apart, and the very fabric of space-time stretches into a vast, empty expanse. In this video, we'll explore the science behind the Big Freeze. We'll delve into the concepts of entropy, dark energy, and the accelerating expansion of the universe. The foundation of the Big Freeze lies in a fundamental law of physics, the second law of thermodynamics. This law tells us that in any isolated system like our universe, things tend to go from order to disorder over time. This chaos is called entropy. Entropy is a measure of disorder or randomness. The second law of thermodynamics says that the total entropy of the universe can only increase. This means that energy over vast stretches of time will become more and more spread out and diluted, like a cup of coffee gradually cooling down as its heat dissipates into the surrounding air. Now, imagine this happening on a cosmic scale. Stars burn out, their energy dispersing into the vastness of space. Galaxies drift further and further apart, becoming isolated islands in an ever-expanding sea of darkness. Eventually, all the energy in the universe will be evenly distributed, and there will be no more fuel to drive any processes, no more stars to ignite, no more planets to form. This is the state of thermodynamic equilibrium, the ultimate heat death of the universe. The idea that the universe might eventually become too cold to support life isn't new. Way back in the 18th century, a French astronomer named Jean-Sylvain Bailly imagined planets gradually cooling down over time, some becoming too cold to sustain life. He called this final state of the universe equilibrium, where all motion and activity cease. In the 19th century, Lord Kelvin, a brilliant physicist, took this idea further. He theorized that all the mechanical energy in the universe would eventually dissipate into heat, leading to a state of maximum entropy where nothing could happen anymore. Kelvin's ideas were further developed by other scientists, like Hermann von Helmholtz and William Rankine, who explored the implications of this heat death for the fate of the universe. Their work laid the foundation for our modern understanding of the Big Freeze. But here's the thing, the Big Freeze isn't just about the laws of thermodynamics. It's also intertwined with the expansion of the universe and the mysterious force known as dark energy. Back in the 19th century, Lord Kelvin was grappling with the nature of heat and energy. He realized that heat wasn't some mysterious substance, but a form of mechanical energy, like the energy of motion. In 1852, Kelvin published a groundbreaking paper where he outlined the second law of thermodynamics. This law, in simple terms, says that energy tends to spread out and become less useful over time. Think of it like a ball rolling down a hill. It loses its potential energy as it rolls, and eventually, it comes to a stop at the bottom. Kelvin applied this idea to the entire universe. He imagined a future where all the energy in the universe would eventually become evenly distributed. In this state, there would be no more energy differences to drive any processes, no more stars to shine, no more life to exist. He called this the heat death of the universe, a state of universal rest and death. This idea was a radical departure from the prevailing view of an eternal and unchanging universe. It sparked intense discussions with other scientists, like William and Hermann. In 1862, Kelvin published another paper where he clarified his vision of the universe's ultimate fate. He described a state where all available energy is converted into unusable heat, leading to universal stagnation and the end of all physical phenomena. But Kelvin also recognized a paradox. If the universe were infinitely old, as many believed at the time, it should have already reached this state of heat death. The fact that stars still shine and the universe is still dynamic suggests that it had a beginning, a starting point from which energy began to dissipate. This paradox challenged the prevailing understanding of the universe's age and origins, paving the way for new cosmological models like the Big Bang Theory, which proposes a finite age for the universe and that it's dynamic and evolving. Kelvin's ideas painted a bleak picture for the universe's ultimate fate. The Big Freeze, as we understand it today, is a descendant of this heat-death concept. Now, where do we stand today with this whole Big Freeze idea? Well, it's complicated. Our current understanding is tied to our assumptions about the ultimate fate of the universe. Think of it like this: we have different maps of the universe, and each map shows a slightly different path to the end. Some maps suggest that the universe is open or flat. This means it will just keep expanding forever, like a balloon that never stops inflating. In these scenarios, we have two possible endings: the Big Freeze or the Big Rip. The Big Rip is a pretty wild idea, and I did talk about it in another video. It suggests that the expansion of the universe will get so fast that it will eventually tear everything apart, from galaxies and stars down to atoms and even the very fabric of space itself. It's like the universe stretching itself into oblivion. If you'd like to learn more about the Big Rip, I encourage you to watch my previous video, which I'll link in the description below. But let's get back to the Big Freeze. If a special number called the cosmological constant is 0, then the universe will keep expanding and cooling down until it reaches the coldest possible temperature, absolute 0. However, our current observations suggest that this cosmological constant is not 0. It's actually positive. This means the universe won't reach absolute 0. Instead, it will approach a slightly warmer temperature, but it will still end up in a state where everything is spread out and there's no more usable energy to do anything interesting. Think of it like a battery that's almost, but not quite, empty. It can't power anything anymore, even though it still has a tiny bit of charge left. This is the kind of heat death we might be facing, where the universe reaches a state of maximum entropy. So even with the positive cosmological constant, the Big Freeze is still a plausible outcome. The universe will keep expanding and cooling down, and eventually it will reach a point where all the energy is so spread out that it's useless for doing any work. Imagine a clock that ticks not in seconds or minutes, but in trillions upon trillions of years. That's the kind of timescale we're dealing with when we talk about the Big Freeze. It's a future so distant that it's almost impossible for our human minds to grasp. Right now, the universe is still a pretty lively place. We have stars blazing with energy, galaxies swirling with matter, and all sorts of cosmic activity happening. But if the Big Freeze is real, this is just a temporary phase. Over immense stretches of time, stars will exhaust their fuel and burn out. They'll leave behind remnants like white dwarfs, neutron stars, and black holes. Even the most massive black holes will eventually evaporate, disappearing into a puff of Hawking radiation. As the universe keeps expanding, the remaining matter will become incredibly spread out. The overall energy density of the universe will decrease and everything will gradually cool down. If the cosmological constant is 0, the temperature will eventually approach absolute 0. But if the cosmological constant is positive, as current evidence suggests, the temperature will level off at a slightly warmer value. Either way, the universe will enter what's called the dark era. It's a bleak picture, a dilute gas of photons and leptons, elementary particles like electrons and neutrinos scattered across an unimaginably vast and empty space. Activity will dwindle to almost nothing, with incredibly low energy levels and timescales that make billions of years seem like the blink of an eye. Perhaps the universe will experience another inflationary epoch, a sudden burst of expansion that changes everything. Or maybe the current vacuum state, the underlying energy of space, will decay into a lower energy state, altering the course of events. And then there are also those truly mind-boggling theories that suggest that over incredibly long periods, entropy might spontaneously decrease. Imagine the universe creating a new universe from the remnants of the old. But the timescale for such an event is so vast that it's almost beyond comprehension. Not everyone agrees that the Big Freeze is the inevitable fate of the universe. There are some scientists and philosophers who challenge the very foundation of this idea, questioning whether we can even apply the concept of entropy to the entire universe. Max Planck, one of the pioneers of quantum mechanics, argued that the phrase entropy of the universe is meaningless because we can't precisely define it. It's like trying to measure the size of the ocean with a teaspoon. It just doesn't make sense. Other scientists have raised similar concerns, that our understanding of the universe is still incomplete, and trying to apply thermodynamic principles to a system that has never been in equilibrium is problematic. Laszlo Tisza, a physicist, argued that we can't argue about entropy for a system that's not in equilibrium. It's like trying to measure the temperature of a pot of boiling water while it's still on the stove. The reading will keep changing. Hans Adolf Buchdahl criticized the assumption that the universe can be treated as a closed thermodynamic system. He argued that we need to consider the universe's dynamic nature and its potential interactions with other universes or dimensions. Even the very definition of entropy for systems that are not in equilibrium is still debated. Some physicists acknowledge the widespread belief in non-equilibrium entropy but admit that it's difficult to define rigorously. Peter Landsberg, a physicist and educator, expressed skepticism about applying thermodynamics to the entire universe without further investigation. He considered the answers to such questions speculative rather than definitive. A 2010 analysis of entropy further highlighted the challenges in quantifying gravitational entropy, suggesting that the observable universe may have more entropy than previously thought, with supermassive black holes being the largest contributors. Lee Smolin, a theoretical physicist, takes a different approach, arguing that gravity actually prevents the universe from reaching thermal equilibrium. He points out that gravitationally bound systems, like stars and galaxies, have a unique property. Their components' velocities increase as energy is removed. This means that these systems don't tend towards a homogeneous equilibrium state, but instead become more structured and heterogeneous over time. Recent experimental findings support this perspective, demonstrating the existence of stable non-equilibrium steady states in relatively simple closed systems. These findings suggest that an isolated system fragmented into subsystems might not necessarily reach thermodynamic equilibrium and could instead persist in a non-equilibrium steady state. We've peered into the icy abyss of the Big Freeze, exploring the science behind this chilling hypothesis and the potential timeline of events that could lead to the universe's ultimate demise. If this exploration has sparked your curiosity, I encourage you to delve deeper into the fascinating world of cosmology. Explore the latest research on dark energy, the accelerating expansion, and the various theories about the universe's ultimate fate. And who knows, maybe the next groundbreaking discovery in cosmology will come from someone watching this video right now. Your curiosity and your willingness to explore the unknown could lead to new insights that reshape our understanding of the universe. Thank you everyone for watching. My name's The Big Y. Don't forget to drop a like, and if you're new to the Why Not family, a follow. And I'll catch you guys in the next video.